we are to discuss the continuity of the function fx at a point at given intervals. This is actually the condition of continuity of the function fx at the point x equal to a. The geometrical meaning is that if we draw the graph of fx y equal to fx, then we will find that limiting value of fx as x tends to a. Now another thing, we find that the function fx is a polynomial function within the interval. If we combine these three, then x is lying in between 0 and 2 as well as less than 0 and greater than 2. Everywhere fx is continuous. Good morning students, welcome to B2S Academy, welcome to my maths class. In the earlier episode, I finished limit and I wrote that I shall start differentiation, but before starting differentiation, I will discuss continuity. Actually, after learning limit, we must follow continuity. That is why first continuity, then differentiation. Y equal to fx be a function. And if x tends to a, then limit x tends to a y or limit x tends to a fx is equal to L. In this case, this limit will exist, already we have discussed. If the left hand limit and right hand limit both exist, that is finite, and each will be equal to L, then we say limiting value of the function fx as x tends to a is L. And we have stressed on the matter that in this case x is not equal to a, and we have not discussed about f a. Now sometimes limiting value of fx may be equal to f a, means limit x tends to a fx equal to fa, means that is L equal to fa. If it happens, then we say the function fx is continuous at the point x equal to. Then fx is continuous at x equal to a. Therefore, when we learn finding limits of given function, just we need only this extra condition. That means limiting value of the function is equal to value of the function at the point x equal to a. Then we say fx is continuous at x equal to a. Now we have to discuss the continuity of the function fx at a point at given intervals. This is actually the condition of continuity of the function fx at the point x equal to a. Now I write, therefore, or so, condition of continuity at the point a L f a is equal to R f a is equal to f a. Means left hand limit of the function fx at a as x tends to a is equal to right hand limit of the function as x tends to a and value of the function fx at x equal to a. These three will be equal, and already we have mentioned that LFA, RFA both will have finite values. Thus the condition of continuity of fx at the point x equal to a is this. Now we discuss continuity of fx at, say, interval AB. This is interval AB. We can also write it as a less than equal to x less than equal to b. I take the closed interval, closed interval continuity of the function fx at or in the closed interval AB. We can express that in inequality form, a less than equal to x less than equal to b. Fx is continuous at x equal to a left hand x equal to b right hand and in a less than x less than b. To be continuous at the left end, that is at the point x equal to a, R f a right hand limit of the given function fx as x tends to a must be equal to fa, and to be continuous at the point x equal to b, left hand limit of the function fx as x tends to b must be equal to fb. Then the function fx will be continuous at the two ends, at left end and at right end. And if the function fx be continuous at every point and fx is continuous at every point in the open interval AB. That means a function fx will be continuous at the given interval a less than equal to x less than equal to b. The function must be continuous at the left end as well as right end. Left end and right end. Also, it is continuous at every point in the interval AB, open interval rather. Then we say fx is continuous in the closed interval AB. Now, number 3, there are more than one functions each of which let the functions fx and phi x be both continuous at x equal to a, then means sum of the functions or difference of the functions will be continuous their product function, that is fx into phi x will also be continuous at x equal to a. Number 3, quotient function, that is fx by phi x will also be continuous at x equal to a. One thing, in this case phi a not equal to 0. If fx phi x be two continuous functions at a given point, say x equal to a, then their sum or difference will be continuous, their product will be continuous, their quotient fx by phi x also will be continuous, and there the restriction is phi a is not equal to 0. Also, the limiting values of phi x as x tends to a both will be non-zero finite. Hence, we discuss here the properties of two continuous functions at the same point. Next, we take few examples. I have taken few examples. Before working out these sums, let me discuss about the geometrical meaning of the continuity. limit x tends to a fx equal to fa. This is the condition of continuity of the function fx at the point x equal to a. The geometrical meaning is that if we draw the graph of fx y equal to fx, then we will find that limiting value of fx as x tends to a and fa, these two are equal. That means there will be no break. Let us take one rough sketch. If we draw the graph of say function y equal to fx, say this is the point x equal to a. After drawing the graph, we find that limiting value of the function, this is the curve y equal to fx, after drawing the graph, we shall find that at x equal to a, or the values of fx as x approaches a from left as well as from right, we shall find there is no gap of y equal to fx. I draw like this. This is y as x tends to a minus, and this indicates y as x tends to a plus, and this indicates this point is a fa point. That means lengths of the ordinates of, here I have drawn 3 ordinates, will be approximately equal. Means there is no gap at x equal to a. In this case, we say the curve y equal to fx has no break at the point x equal to a, hence fx is continuous at the point x equal to. This is the geometrical meaning. Now we work out these problems. Number 1, fx as given when x less than 0, value of fx is minus x. When x lies in between 0 and 2 along with the extreme values, value is 2, and when x is greater than or equal to 2, value is 4 minus x. We have to discuss the continuity of the function at x equal to 0 and x equal to 2. First we consider x equal to 0. Now first we calculate LF0. LF0 means limit x tends to 0 minus fx limit x tends to 0 minus, when x less than 0, x tends to 0 means x is less than 0 but near to 0, value is minus x, and naturally the value will be 0. If 0, you see x lies in between 0 and 2 along with the extreme values. In that case, f0 is 2 and rf0 limit x tends to 0 plus fx. That means limit x tends to 0 plus, in that case fx will be this one, 2. Therefore, we find LF0 is not equal to F0, and though F0 is equal to RF0, but the condition is not fulfilled. Actually, for continuity at the point x equal to 0, we must have LF0 equal to RF0 equal to F0. Hence, we conclude fx is not continuous at x equal to 0. And now at x equal to 2, we calculate left hand limit, and we find that limit x tends to 2 minus fx. 2 minus fx, that means we have to consider this interval. The value is 2, therefore limiting value is 2. Then f2, from this f2 is also 2. And rf2 limit x tends to 2 plus fx. Here we have to use this one, x greater than equal to 2, 4 minus x therefore LF2 equal to F2 equal to RF2. Therefore, fx is continuous at x equal to 0 and 2. Now another thing, we find that the function fx is a polynomial function within the interval. If we combine these three, then x is lying in between 0 and 2 as well as less than 0 and greater than 2. Everywhere fx is continuous as fx is polynomial function.